Yeah, good morning, everyone. So am I clearly audible?
Good morning to one and all present here. Welcome, ma'am. Pooja Das, ma'am. Am I audible, ma'am?
Yeah, good morning, ma'am. Yes, you're audible. Am I audible?
Yes, you are audible, ma'am. So this is a 5-day FTP on recent trends in electric vehicle technology. So 4 sessions we have completed from starting from 19th, that is on Monday. And today we are at the end of the session, 5th day. So we are having Pooja ma'am, Dr. Pooja ma'am with us. Welcome you, ma'am. I would like to read her profile just for a second. So Dr. Pooja Das ma'am received her PhD from NIT Tech, and she has 15 years of experience in industry, R&D and academics. Currently, she is working as manager, Power Research and Development Consultants Private Limited, Bhubaneswar, Odisha. She published papers in various international journals and conferences such as IEEE, Springer and elsewhere. And she is member of various technical chapters. She is skilled in MATLAB, Python programming language, engineering research, and C programming language. And her area of research interests include power systems. And she has co-authored 2 textbooks. And I welcome you, ma'am, for this session. It is a great privilege for us having you with us. Thank you, ma'am, for accepting our request. You can go ahead with your session, ma'am.
Thank you, madam. Thank you for this great introduction. My screen is audible.
Hello. Second page highlighting
I think, yeah.
I request participants to mute themselves. Request participants to mute yourself.
Number and madam,
I have muted, ma'am. Please continue, ma'am.
Okay. Ma'am, my screen is audio visible.
It is audible, ma'am, but a bit low. If possible, you just increase, ma'am, mic volume.
So I hope it is audible now.
Yes. Yeah, audible, ma'am, and screen is also shared.
Okay. Yeah, good morning, everyone. Today I'm going to present on the topic of microgrid control strategies towards sustainable energy management. And I'm also going to give a discussion about the low frequency control of a grid-connected microgrid in presence of electric vehicle. Actually, the 4 days of FDP completed, so many topics, advanced topics in the electrical vehicle has been completed. So I thought to skip that introduction to electric vehicle, types of electric vehicle. Hope you all people aware of this all topics. So today, what is the aim of the presentation? Actually, as it is a particularly what are the recent trends and technologies of particular research is going on the field of particular electric vehicle. So based on that, and all the audiences are, most of them are the faculty members. Those are pursuing their PhD, MTechs, and pursuing PhDs and also guiding the MTech students and having the good research atmosphere. So I thought to give some particular glance on particularly what the recent trends are going on in particular research field. So for that reason, I have chosen this topic, which is a microgrid. First one is a microgrid control strategy. Just a basic introduction I'll give about the basic control strategies. Then we'll go for a small study, case study. So this is particularly the content of this presentation today. For the basic introduction, classification of microgrids, types of particularly important types of microgrid control methods. So many methods are there. In general, I just categorize some important methods and one case study, which is based on the genetic algorithm, which is intelligent-based algorithm used for the load frequency control of a connected microgrid in presence of electric vehicles. So we know the microgrid, no need to give the definition of a microgrid. As we all people know, the microgrid technology exhibits attractive features such as the high power quality, reliability, sustainability, and the environmental friendly energy to the consumers using the control and energy management systems. These are the main key features, particularly while we're using the microgrid is so advanced and particularly very now it is come to the very limelight for in the field of the power system. So generally for the adoption of distributed energy sources and particularly what will be happening, we know the energy transmission through the utility power grids will changes, which provides a flexible energy utilization for the consumers. And also another hand, also we also know the high dispersion of the distributed energy generations like DGs and EVs into the grids bring a big challenge to the operation stability of the power system nowadays. Not in India, we cannot say, we can say in the point of EVs. But of course, yes, distribution generation means what is widely used and a lot of penetration of this particular distributed energy generations is a big challenge for the quality and reliability, in general reliability of the power system. And if we're talking about the electric vehicles, particularly European countries, American countries, they are using a huge amount of electric vehicles. So charging is a big challenge. Some months now, new recent technology, instead of battery energy storage, we are giving power backup to the microgrids, particular small microgrids or mini grids with the EV vehicle as like a power backup strategy. So those are also very important factors while we are going to consider this particular reliability in the present power systems. So, for this, different microgrids are there. In general, if we'll say microgrid in terms of supply, it's AC microgrid, hybrid AC-DC microgrid, or coupled microgrid, you can see, and DC microgrid. And also with the voltage tables, also you can also categorize a different type of microgrids. So I think is it clear? Okay, fine. So we can also categorize the microgrid with respect to the utilization, generation level, voltage levels, and also application level, supply level. So if we talk about the AC microgrid, generally MG is what the I think we're using for the microgrid AC microgrid. So here this is the main grid as we can see, and this is a particular the microgrid, and it is connected with the PCC point of common coupling. Generally, it is a point of interconnection, POI or PCC, you can say. And this is connected through a switch, particularly either is a grid following mode or means what, or you can simply say it is a grid connected or islanded mode. So this is a particularly the microgrid side, you can say. So here, what happened in the AC microgrid, whatever the generations and all in the particularly the distributed energy or particularly photovoltaics and all loads are AC. We have to convert all the generations into the AC form. Again, we are going to utilize. So particularly this is a during according to the applications of the load, we can call as a AC microgrid. It is easy to integrate, but thing is what due to requirement of large and complex power electronics interfaces, particularly in AC microgrid, gen losses are more and harmonic impact is also there. So next category is a DC microgrid. Obviously, whatever the source, particularly DC sources, whatever they are either wind energy, whatever the voltaic cells, whatever the generations we have with the battery directly, the loads we can use in the DC mode. Right? And also you can see here also there is a point of common coupling is there. So AC is converted to DC and particularly the loads are DC. So here thing is what here also whenever it is a grid connected mode, we are going to refer to the POI or PCC point of common coupling. And here is a DC and DC converters are used for the voltage booster purpose. Here thing is what is a simple structure controlling requirement can also very is what quite simpler and also improve the efficiency of the system. So reliability issue arises in this type of microgrids because of use of Power-to-X converter due to the serially connected in the system and leads to inefficient handling of the power flow from the distributed grid. So here this is also one scenario, on which the research can be processed. And next is a hybrid AC-DC microgrid. Here, particularly in this type of grid, both your AC and DC loads are there. And according to the applications or according to the utilizations, particularly conversion mechanisms are also there. So here the controller for various converter in this particular hybrid microgrid, and these are called the hybrid microgrid, is essential to ensure the stability and efficiency of the microgrid. Right. So in general, this is the basic definitions or description of particularly the basic types of micro with respect to the type of load. So if we'll go for the summary in one, we can say. So in particularly AC microgrid, open relays, declosures, these are the protection schemes we are using. For section riser, minimum circuit breaker, SCVs, MCBs, fuses. And whenever we are talking about the DC microgrid, it's a utility protection list, fuses are there. So model case circuit breakers are there, power circuit breakers are there, static switch, and isolated cases are there. So whenever you are talking about the hybrid microgrid, so we are all talking about the AC and DC links which are connected through the two transformers or to 4-quadrant operating 3-phase converters. In general, this is the basic configuration, whatever I am discussing here. So whenever you are talking about the voltage conversion in AC microgrid, it is a AC, DC, AC converters for the stable coupling. AC load directly to the bus line. This requires AC DC convert for the DC ports. Whenever talking about the DC micro, this is a bi-directional DC DC and DC AC inverters are we are using, particularly power converter connected to the bus line. So whenever talking about the hybrid microgrid, so it generally uses the transformer for the AC side for the voltage conversion. You use DC-DC converter for the DC side for the voltage conversion. This is all about the voltage conversion for the infrastructure or technology you are using. So whenever talking about the integration, particularly in the AC micro, it requires the conversion label to integrate with the DC DG units. AC needs synchronization, integrated with the high frequency AC DG units. So whenever talking about the DC microgrids, easy to integrate with the PV cells, wind turbines, and fuel cells. Generally, these are the particularly whatever the resources we are using for the power generation, particularly in the microgrid side. And in the hybrid microgrid, whenever talking, so direct integration, it is a direct integration suitable for the DC-based generation. So example, PV electric vehicles, fuel cells, energy storage. So there we are preparing this particular hybrid in a microgrid system. And it does not require any power converter. According to application, we'll go for the configuration. If you talk about the advantages about all these microgrids, so whenever talking AC micro, easy configuration by existing grid, required synchronization of the DG. So when talking about the DC microgrid, DC ports can connect it directly to DC bus. So low number of particular power converters are required. As we have talked about here, controlling is very easier, simpler. When talking about the hybrid microgrid, it's a direct connection to the grid. It does not require synchronization of the DG units because it can directly connect it to the AC or DC network. Controllers are simply reduced energy losses. So talking about the disadvantages, we can say easily, we know all those things by our research and studies, the difficult synchronization with the host grid while maintaining the frequency, phase angle, and the voltage magnitude. So for that reason, AC microgrids are showing the low efficiency and reliability, complex architecture, and control. Whenever talking with the DC microgrid, voltage is not standardized. So require additional power stage to generated AC voltage cannot be reconfigured from the existing grid or whatever you can say the hospital. So protection is complicated. And whenever talk about hybrid microgrid, it's a low reliability, complete controller and management, especially in islanded mode, combined architecture of AC and DC microgrids. So we cannot say this is the disadvantage. This is actually you can say these are the limitation where we can improve the particularly grid structure and controlling structure, energy management structure, load management, so that we can go for a right means what a great power system, power network in the coming futures. And a lot of scopes are there, and we can get our scopes, particularly for this limitation, or we can say the disadvantages. So these are all about the particularly. So I want to come back to the screen actually. So this is a very clear that we know about different type of microgrids and all. So generally people are saying what are the advantages and disadvantages.
Excuse me,
Whatever-
ma'am.
Yeah.
Your screen is not shared, ma'am, right now.
No, actually I stopped actually sharing.
Yeah.
So I want to discuss something and I'll go for again sharing.
Okay, ma'am. Okay, ma'am.
Okay. So thing is what whenever people are feeling disadvantages and all, it is my personal opinion, we'll get all the particularly the scope or particularly what are the research future scope from those limitations only. So whenever we'll overcome those limitations and make the system more reliable, so we can find a great power system or great network connectivity, and we can also particularly utilize the maximum to maximum renewable energy sources. So for our particularly the consumer particularly requirements. So here one important thing is whatever I found during my research and studies and all, mainly control of real power flow, reactive power flow, and controlling of the voltage frequency. Those are the very major facts. Whenever you're talking about the microgrid, which is connected to the particular host with the main grid. Excuse me, 1 second. Yeah. So, particularly the real gas power flow control, whatever I told you, the voltage control, the frequency, and controlling the frequency and adjusting the standard frequency. These are very important fact whenever we are talking about the grid connected to the main grid. So I did more, particularly some controlling techniques are there for some controlling some factor. So nowadays, a particular distant power system, all the microgrids they're planning to connect it to the grid so that we can go for the bi-directional flow whenever where it is a requirement. So controlling methodology or mechanism for the microgrids is very much important. Next topic is for particular energy management. This is also another major fact because whenever we are talking about the microgrid, we are talking about particularly the generation of solar, wind and all. So those are generally whenever the microgrid or particularly non-renewable energy sources will come into picture. So clearly it will bring the particular energy resources, particularly energy storage devices into picture, a very clear form. So how to manage the particular battery energy storage for the or management in the grids, whenever it is either islanded mode or maybe it is a grid connected mode. These are the two important points, whatever we are creating for particular microgrid, all the connections. So next thing is what whenever talking about the microgrid control, so you can, I think, is it clearly visible? Yeah, my screen is clearly this, so there's particularly the tree diagram is clearly visible.
Madam, is it visible, madam? Visible.
So whenever you are going for the microgrid control methods, so you can categorize first into two methods. One is a conventional control method, one is advanced control method. So whenever talking about the conventional power methods, the loop control techniques will come into picture in the first. Then you can say the virtual impedance loop based loop control. Then master slave control technology, multi-agent pest control technology, maximum power point tracking control techniques, MPPT. So loop control, again, it may be a conventional loop control or adopted loop control. Conventional means it is a high inductive blind impedance control, large inductive filters are there for the controlling mechanism. Whenever talking about the adoptive loop control, it's a single phase inductive MGs, three-phase inductive MGs, so second order filter derivative terms based on techniques, algorithms, and optimization based techniques, theory based. So are the fields where you can touch and you can go for the loop control mechanisms. So whenever talking the virtual impedance loop control, so in this single phase inductive microphase, three phase inductive microphase. So single phase inductive microphase, you can go for the high pass filter designing. Three phase is zero steady state either virtual transformation based controller. These are the methodology or different type of strategies we are following to put the controlling mechanism. So whenever talking about the master step control, it's a micro source load share. This is a very important factor, and massive inverters and slave inverters, those are the two parts of this particularly master step control. Next, the multi-agent based, which is a general representing the decentralized coordinated control. Here, graph theoretical topology model is there, non-cooperative dynamic game model is there, genetic algorithm, particle swarm optimization, different type of means what we can say the heuristic automation techniques are also there. So then we can say for the maximum power point tracking, this is a very common to the researchers who are working on the particularly the field of solar. So tracking techniques with constant parameters, tracking techniques with measurement and the comparisons, tracking techniques with tracking techniques with mathematical calculations, tracking techniques with the intelligent predictions like a fuzzy, AMM, or different type of algorithms like a genetic algorithm, yes, custom optimization, Firefly, bad algorithm. So many meta heuristic algorithms are there. So this is all about the conventional control method. So whenever I talk about advanced control method, we have modified the conventional methods and we are going for advanced one. First one is centralized control. Here, microgrid central controllers are there. Microsource controllers are also there. So in particularly, whenever we're talking about the microgrid central controller, we can go for the voltage source converter or PQ inverter controller. So next is a microgrid supervised control, which is a decentralized control techniques, and which will follow multi-agent based techniques, distribution network operation based technique, which is called as a DNO, then market order based techniques. Then next come to hierarchical control. In hierarchical control, primary and secondary controlling mechanisms are there. In primary, grid following control and grid forming control. So next is the secondary control. In secondary control, you can say centralized management and centralized management. Another hierarchical method, another is a tertiary control, which is a centralized management or distributed management. Next, when we talk about the advanced control mechanisms, so intelligent techniques is a picture. So in a microgrid, intelligent techniques can use a fuzzy logic controllers, artificial genetic algorithm, tablet algorithm, object neurofuzzy interface system, vertical swarm optimization. Now you can see also the particularly machine learning come into picture, because it's a controlling accurate prediction and controlling mechanism. And when you have the adaptive techniques, it's a adaptive proportional integral derivative PID controller, adaptive sliding mode controller, reinforced learning, model predictive control. Those are coming into picture. And also interesting factor there, we can also use the particularly metaheuristic algorithm for optimization techniques and fuzzy ANN, and particularly whenever you can say it is an AI modulated control also. So this is all for the different type of controlling mechanism. So I have chosen this four important method, basic method technology based on particular the microgrid control is a group control method, master step control method, multi-agent based control method, maximum power point, ABPD control. So group control method generally whatever we are doing in the group control method, where method aim is to what the adjustive both the adjustive active and reactive power. So there is a PQ power means what real and reactive power control and also the power quality. So output of basic frequency and voltage, you can say whenever the real power will mean for the frequency control, whenever we're talking about the reactive power control, we basically mean for the voltage control. What is the multi using the communication links and the parallel connected converter. In grid connected mode, which is the grid following mode, generally called as grid following mode. The main objective is to ensure the efficiency of the energy management system. Here, EMS stands for the energy management system, which is organizing both the energy production or dispatch and scheduling of each device. So in islanded mode generally is known as forming mode. The goal is to control or maintain the voltage and frequency of the system within a specific prescribed limit of the vehicle. So hence what is the happy output of the
अच्छा आगे लेकिन ये ऑलरेडी हाँ ये ऑलरेडी जमा कर दिया अच्छा फार्मेसी एक बार नंबर मैंने को मैच हाँ हाँ एक बार बता
I think some disturbance is going on. Can you please mute? Yeah. So what is in general what you can say the aim of the control is both maintaining the particularly voltage frequency and amplitude of the inverters must be able to independently compensate it for active and reactive power imbalance by load sharing. They are limited by their low transient responses that requires a low pass filter, unbalanced sharing of harmonic currents, and the inherent trade-off of voltage and power sharing. Yeah, can you the troop control meter each unit uses the frequency to control the adequate real power flows instead of the power and phase angles because of the uncertainties in the initial phase mechanism of the unit in the standalone system. We can say it is a 10 different change in frequency to engine voltage. So frequency real power flow and voltage reactive power flow will change in voltage. So this is the troop control strategies. So generally DQ control mechanism, current control we are using for particular this DVR control. So you can also go and have a study about this troop control mechanism. Now so in particular, this troop control mechanism, now particular for CPS troop control mechanism, and this zero for CPS troop control mechanism. It's a rando means what is a very recent research interest, particularly in the microwave control mechanisms. You can also get so many papers, recent research papers in particular on this methodologies. And also you can go for the different resources with the presence of electric vehicle, either vehicle to grid or vehicle to vehicle or a vehicle to home. This is the another technology. We need G to V, V to G, and vehicle to H, V to H. So in those also we can go for in a particularly hybrid microgrid or particularly we can go for this particularly the troop control mechanism, the different variations of the particularly the electric vehicle, different scenarios. So this can be an interesting study. Or many researches are also going on that the scope is also there. So when you were talking about the master slave control methodology, so obviously one is a master, one is a slave. So here, like particular inverters, we are just categorizing on this way. So these are the particularly control comprises microsources as a major element in coordinating the operation of the interface converters of each DG. So once the microgrid is connected to the grid, all the microsources contains the master converter, which provides the voltage and frequency references. For example, when the main power supply is lost or when a power outage event occurs, the slave takes the voltage references from the master and works in PQ mode. So low voltage microgrids with the master slave architecture, which covers interaction between the utility and microgrids at the point of common copy generator is proposed. The grid connected mode, particularly the grid works as a master and the master converted in the engine. The microgrid acts as the slave with the central command unit generating references control signals. So different scenario, some parts become the master, some parts become the particularly the slave. And thing is what in a suppose whenever talking about an island, what happened? The master DG operates as a voltage control source, while all the slave DGs units operate as the current control sources. So therefore, a reliable and fast communication link is very much important whenever you are talking about the centralized control unit to particularly send the comments to all the DC units efficiently so that they can act accordingly and efficiently, particularly in this particular master slave control. Another is a multi-agent system. Or it's a it's mass-based control method. What happened in the mass-based control method is widely used for the microgrids. So generally, fully rooted in decentralized control, in which two or more interacting agents follow their own rules and goals and, and perform function autonomously. So particularly in this multi-agent system can control and stabilize voltage output, frequency and power with a changing environment and load with uncontrollable renewable energy sources. So one strategy is to get the power sharing between the ultra capacitors and batteries distributed in the particularly DC engine. And particularly when we're talking about decentralized coordinated control scheme based on the mass has also been proposed for the micro. So similar control frequency is also employed in the island and microgrids. So what you can say the advantages particularly, they include the ability of the overcome uncertainty systems, to improve the efficiency information sharing in decentralized manner. So these are mainly what happened. You can see there is the first decision making process and the operation. So whenever there's a, as you can say, the decentralized, so you can also wherever particularly any disturbances are coming, it can take its own decision and can go for the immediate controlling action. So particularly whenever as you can say the agent, particularly what it includes the electrical equipments such like a battery energy storage, wind turbine, gas turbine, load monitors, particularly loads, particular for the gas turbines loads. Your gas turbine, as mentioned, it depends upon the what is the type of particularly source is there in the main. It may be a hydro, you can say. Generally, a thermal based system is taken as the basic system or standard system. So your gas turbine is mentioned. And also it also after means what it includes this equipment, electrical equipment, so electrical parts. With respect to that, it also monitors the status and controls the operation of the electrical devices under the coordination by the microgrid central controllers. You can see here is a PV. Particular PV source it has been taken as source. This is a load. So this is a converter as it is this is DC or DC voltage of the PV with respect to load, it's a PW generator, so it is a control. So here thing is what this agent so controlling mechanisms are there with the multi agents. So here also one controlling technology is there. Here also one controlling, and there's all are is what. Here in the MPPT is mentioned temperature sensor and irradiance. This is only for the MPPT. So as I have said here, this ways of what is generally multi-agent. Multi-agents are there to taking care of the stability and security of the particularly for the so next is a MPPT controller. So MPPT controller, as we know, the maximum power point transfer controlling mechanism. Generally, this has been introduced in particularly solar PV systems to extract the maximum power point. So controllers are the for the MPPT, as we know, for the it's a programming based, in which condition maximum power can be, but particularly can trace to save the performance or store the power to the maximum. Here, technologies now they're using the different type of center meta heuristic techniques, particularly intelligent AI based techniques, fuzzy based techniques for the MPP, maximum power point tracker or MPP technology or methods. And now it is not only related to solar or wind or something. Now, whatever we're using, where fuel cells are also coming into the picture, thermoelectric devices are also coming into the picture, where you can also go for the MPPT controller for the to harvest the particular maximum energy from the out. So generally, whenever talking about the advanced microgrid technologies, we can take in microgrid supervisory controller, centralized controller management, decent microgrid management, primary, secondary, and tertiary control. These are coming into advanced control technology. So whenever supervisor controllers, they're categorized centralized and decentralized. We aim is to provide functions such as power quality control and to optimize the system operation by enhancing the intelligent variables. The following section particularly next is decentralized centralized control management. Centralized control management provides a strong supervision which includes a straightforward implementation real-time observability of the whole system. It requires data from the microgrid component and the external grid to execute the optimization procedure for the efficient operation of the micro. Here I can say particular centralized machine learning technology will give a very precise and particular. There's a lot of scope of machine learning application, for example, for the data calculation, data manipulation, and so this is centralized microgrid controlling structure. You can see the load capability, provide load capabilities, local controllers are installed, controller loads. As a feeder, feeder, three feeders are there. So local controllers are there, LCs are there, which is mentioned for the sensitive loads. Microcontrollers are there for the DGs. Access controllers, these are the local and popularly. This is a microgrid sensor controller. The local controls are commonly used for the distribution energy unit. The main microgrid controller unit optimize the operations. The micro resource controllers and the local controls follow the order of particularly order and are independent on this particularly MGCC, who is the microgrid central control in this particular controlling scheme and perform their own control autonomously in island. So as part of the utility of the microgrid system, DMS or distribution network operates also interference with the MGCC to manage the operation of medium and low voltage areas if multiple MGs exist. So this is simple configuration and the work operation. So when we talk about decentralized management, so decentralized management enhances the flexibility, expandability, and has emerged in the microgrid systems. So the controller allows for great flexibility of operation and also avoid a single point of failure because of log and play function. So frequency and voltage regulation, DR coordination and energy management can be realized in a decentralized manner because of the level of decentralization. In decentralization control, particularly the MCs are mainly responsible for the maximizing their production for demand satisfaction and expansion to grid given current market prices. So this is all about the particularly this is depend upon the what are the structure, what is the type of particularly what is the aim of the particular controlling mechanism is showing. The purpose is to automate the microsources and local particular load maximum. So one interesting research on this supervised control is the employment of multi-agent system-based DMS. This is a very interesting research field. We can also pursue this particularly given interest. So MES is a system that consists of multiple intelligence systems that provide the local information and interact with the other to achieve the multiple global and local objectives of the. So a lot of particularly researchers are going on this particularly mass-based TMS system. So this is the hierarchical control mechanism. Primary inner loop control, primary control, secondary control, tertiary control. So this is a particularly important export, particular power exchange informations with the main network, restoration of grid synchronization. These are the functions, which is the compensation of the voltage and frequency deviations caused by the primary control. independent local controller for increasing the reliability, which is the voltage and frequency stability provision, managing output power of the renewable energy sources. So in hierarchical control, it operates in both it's micro, it's a micro, and this is composed of tertiary, secondary, primary. The purpose is to provide a control over the production of power from the renewable sources. So you can already see grid connected mode of the microgrids. Particularly, it's based on the IEEE 1547 standard, which is introduced in 2003 with the proper implementation of the detection algorithm for the system transaction into both the microgrids particular supplies that require active and active power, stable frequency, and can operate within the specified limit of voltage ranges or limits. So again, this is a primary control and the secondary control and the tertiary control. So whenever talking about the primary control, this follows through grid following mode and grid forming mode. So I'm directly going to grid following and grid forming mode. So generally, what happens in the grid following mode? The voltage and the frequency of the micros are controlled by utility grids with the grid connected mode. Already grid following. So it is a grid main grid connected. So hence the purpose of the grid following control is to optimize the power sharing strategy of the network because of the local controllers of the REC operate with the current control mode to extract the maximum power from the energy sources. And wherever talking about the grid forming mode, that means what is a microgrid is there, or you can say micro operated. So an optimal active and reactive power control should be realized to provide the adequate power frequency or power sharing between the DG and ESS, energy storage units, and their best frequency of the AC. The microgrid is spatial under the 100 mode. It's called the grid farming, how it functions. So many for means of configurations or two configurations are there. Single grid forming, multiple grid formers. The secondary control is either centralized or decentralized. So the of the load is controlled by central control, MGCC. Centralized management. But still, the tables. The secondary centralized control is control levels on the basis of the tertiary control levels when operating the mode connected. Non-centralized or decentralized mode. In this strategy, the power the microgrid centralized in the microgrid central controller integrated with the load controllers network with the tertiary control level. So disturbance event, the faulty units. So this communication network such as the this strategy. Now communication and communication networks are common. So the taking order, the distribution control and trade control. Available again, this is also centralized and decentralized, particularly in the tertiary control, decentralized management. The power values at the PCC, which interfaces with the utility grid. The power quality basis of different values. So achieve an optimal is the main function. So whenever talk about centralized PCs to main grid, example in SCADA, some studies suggested that last of the knowledge, the ancient intelligent techniques There are certain technical techniques we're using for particular market control the particular market. Exact particle form optimization, materialistic different materials techniques, that are neural networks, model predictive control, reinforcement plan. All this will come into different type of PID control, adaptive controller, adaptive sliding mode controller. They all will come into this particularly MG induction techniques. Excuse me. So we know particularly this intelligent techniques are particularly most of the researchers are going on based on that. We are comparing different optimization techniques or different intelligent techniques to particularly to controlling our parameter and getting a better voltage profile and frequency profile, particularly reactive arc profile, particularly the system with a different scenario. So, for example, so many methodologies are there here, particularly one secondary control scheme. I have just opt here for the simple classification, simple explanation of this particular data techniques. So here one case study I have taken the genetic algorithm based low frequency control of the grid connected microgrid in regions of electric vehicles. So here I want to say the electric vehicles are going to give supply to the grid, like the electric aggregators are there. So objective is that connected microgrid with hybrid generation system consists of thermal power generation, which you can say as a particularly the grid main grid or grid connected mode with the solar photovoltaic cells, wind turbines, geothermal power plant GTP has been studied with the different combination of EVs with EV aggregator. So a rare participation factor based on EV aggregator has been modeled with the presence of a different number of EVs. Genetic algorithm has been opted for the optimization of the controllers. So dynamic analysis has been done here in this particular league. We are going to discuss about the dynamic analysis with the step of automation and the angular automation. So this is the general system popular. You can say this is the microgrid, central control FCG, stability control, the frequency energy management, change charge demand, coordinate control, flow control. These are the control method. Here aggregated control center is there. This is the EV aggregator. These are the loads, which are thermal. This is the solar power plant. So these are the different units of the system. Here, what are the charging demand, particularly it will go to the aggregator control center, and also aggregator control center will give a signal to charging power allocation. So here also the bidirectional control mechanism or particularly information are passed into the MGCC. And with respect to that, it will be going and controlling the particular power. Mainly depend upon this, it will going to control how much power it is going to take. And what is the availability of the net power in the EV aggregator. EV aggregator means what? So many electric vehicles are there and connected in series and parallel. So forming a source of supply. So this simple transfer function model is there. So I'll go to that before. Before that, I want to put in the aggregator. So an electric because he or battery energy with some capacity which general would take into this. Now EV aggregators are the particularly intelligent management of EV aggregators and particularly compensation of the power source inverters with the help of EV aggregators. So here so many EVs as we can see. So many EV entities are connected in series and parallel and giving supply to the distribution network and all discharging is there. It is a calculated and how much the system requires in how much power is going to be given to the aggregator for the charging purpose also. So you can say the EV aggregators are responsible for the owner with their order and also maximizing the profit of the power So the electric vehicle want first than power plant because it is a magnetic and mechanical process. An aggregator model is the battery charge, primary frequency control of the and frequency control is taken. This is the block diagram. This generates the plant there. This is the EV controller. Power and thermal power. So we are considering this a green mode and also solar system. Yeah. So system.
Hello, ma'am. Your voice is disconnected. Hello, ma'am. Hello, ma'am. Pooja, ma'am.
Yeah, am I audible? Yeah, sorry, yeah.
Yes, ma'am. Now
So
you're
audible?
audible, ma'am. You can share your screen also, ma'am. Yeah, yes, ma'am. It's
So
discussed.
as you discussed, yeah, we can discuss here this wind power plant transfer function model here. The particular this is a solar photovoltaic system. This is a geothermal. This is a thermal power plant. So this is a you can say this is a power system which is all our sources are connected. This is the ID general particularly you can see uses the cost function. Here two controllers are there, decentralized controllers are here. One controller is a plant controller, which is controlling the particularly the power balance with respect to the load, and also here another EV controller is also there to give the signal to the EV aggregator how much load power it going to be shared to the system for the compensation purpose. So it is also getting the particular signal for the system for the power imbalance. So as you can see here is a plant controller and EV controller. We may use here simple I integrator or PI controller, PID controller, or you can use the particularly different type of now cascade controllers or particularly whatever is called fractional order controllers or fuzzy controllers. So here you can use the different mechanism, and you can also comparing particularly your system and resources I have taken like here. We may also take different other resources, like instead of wind, I can say take the fuel cell power. Solar also you can take. You can take geothermal and thermal. You can take also hydro also with the different type of power scenarios. What is the according to availability? So you can take the different power sources. And here the step disturbances we are feeding here. You can take the step road perturbation as a basic reference or standard particular disturbances, or you can take the random load perturbation based on the load demands. What is the total 24-hour scenario for 10 hours or 5 hours time being? What is a particular load variation in the load with respect to that also you can take this particularly random load variation instead of a state load perturbation. And in the cost function also here integral IDE we have taken, you can take integral square area IAC. So many type of cost functions are there with respect to system. We can also compare the particular type of cost function with respect to the cost function, how the particular error is minimized particularly. So here error is what we can say particularly whenever taking with this system, it's a you can see here. So frequency is only the deviation here. So you can take the frequency. Also, you can add the voltage control also. So change in frequency and change in voltage, maybe the deviation, which is the errors, is going to be fed to the plant control. And with respect to the deviation, it will control the particularly generation. Here, it will take the power from the particularly main source or grid. This is a grid to the system, or it will take the power particularly, as you can see, so with respect to the solar and wind, what are the powers that are available to storage. With respect to the rest of the power, it can take from the main grid. Right? Also here in the EV controller, what happened? So it will take the feedback, how what is the deviation, what is the control error, particularly is going to fit with the control. It's also same in voltage change and frequency in this particular system. Also, we may add the change in voltage also. You will see how much the deviation is there and how much power it is going to be. Means what segregate from the particularly EV aggregator with the availability, and it will give a fit to the system for the compensation or load balancing, generation load balancing purpose. So this is the automatic load frequency control, particularly of a grid connected microgrid with presence of EV aggregator. So what happened in the EV grid aggregator? So many EV units are there. So already we have discussed about the EV aggregator, how many EVs are there with respect to your system, how much power is available, because it depends on the charging and discharging of the EVs. How many EVs are there ready for the giving the support to the load system, particularly the microgrid support to the power system by supplying the power. We have to means what is particularly it will be calculated, and that much of from that available power only we take the power. So these are some parameters we have taken here. I'll just share the slide with all of you. For this transfer function model, these are the particular values we have taken for the different type constants and gains. So we have designed the system with the Indian frequency 50 Hz. So it is R is a speed regulation from 2.5 Hz per unit kilowatt. So it has been taken. And also another important thing is what here, particularly in solar cell also with different irradiances also, you can also take the different study can be done. I have given only a simple study with the constant irradiation. Here you can change the irradiation. So wind also you can change and you can go for the different scenario studies. Here I make all this thing constants, only have changing the number of EVs, and we are just checking that what is how much, in which way it will compensate or you can balance the change in the load with the load generation balance. So different scenarios or different case studies you can take here. Controller, simple I have taken the three controller, the PI, PID, and controlled by the genetic algorithm GPID you can see, and its aim is to control the parameters of the particular controller to minimize the error. So controller comparison also, there is a feasibility possibilities that there in that particular state. Different other controls also you can take like a 2 degree of freedom, 3 degree of freedom controller, a different combination of the cascade controller. Or I can say you can we may use the model predictive control, we may use the particularly different control, whatever the new control technologies are, the secondary controllers are there, we may use. So this is a particularly genetic algorithm flow chart. So as we know, the particularly genetic algorithm is chromosomes. We have to first choose the number of generations, initial random population of chromosomes. You have to choose generation first. We fix as to 0, then you go for the increased number of chromosomes. Here, this is dependent upon the KPKI KD values. Then evaluate the fitness of each chromosome in population, that is a fitness value, which will be based on this particularly objective function, which is a replica of the objective function or JIDE calculation, then selection, crossover, mutation. Or here you can check the maximum generation. If yes, you can go get the optimal value. If it is no, again we will start the process. So this is the insurance genetic algorithm. As we all, I hope all people will know all about this genetic algorithm because it's a very basic algorithm used in all optimization techniques. So this is the simple PID controller we have taken here. So parameter here, number of population we have taken 10, percent 20, generation 2, crossover, SBX we have taken, mutation polynomial mutation we have taken, selection tournament selection, k is equal to 2 value we have taken, crossover distribution index we have taken 20, mutation distribution index we have taken 20, probability of crossover we have taken 0.8, probability of mutation we have taken 0.2, bounds lower limit and upper limit we have taken as 0. Here the upper limit and lower limit we can fix with respect to how much the control gains you want, particularly the PI, PID, how much controller you are using. With respect to that, you can also fix the lower and upper. We generally fix as 0 and 1. So generally these are the studies investigated without EP and with EP. Without EP, whatever system with the different scenarios with the different load disturbances, and with EP, how it is improved. Then we have actually here we have created a step load perturbation of 1% at 4 seconds. Sorry, some disturbance is there. So coming to the EP aggregator, N1, N2 means 2 entities we have taken to the aggregator. So first we have taken 80 numbers of EVs. So N1, sorry, it is a disturbance from my side or now it's okay. So here first number of 80 number of EVs are were taken. The first N1, the particularly aggregator set, you can see come to here. So this is N1, this is N2, two aggregators are there. You can see aggregator 1, aggregator 2. So N1 representing aggregator 1, N2 representing aggregator 2. So one combination we have taken 30 plus 50. So in aggregator 1, 30 number of ABs are there, and 2, it's a 50 are there. It depends upon how much, it's just like we have taken by manually. based on assumptions. We can also take the number of EVs, charging, discharging, SOCs. That's what charging labels. Also, you can decide how many EVs are available to give a support to that system. So next is the 160 number of EVs we have considered 160, and third is a 300, 100 and 200. Like a different combination of EVs with the aggregators we have considered here for the study. And dynamic PID tuning we have done. So directly we can go for the system study. You can see here. So this is the 1% SLB step perturbation we have considered. So this is the with and without EV. You can say without EVs. This is the PI without EV controller comparison has been done here in this particularly frequency deviation. I think picture responses are clear. So the blue dashed lines are the PI control without any presence of any EV. The black dotted line represent the PID controller without any EV, and red line with the genetic algorithm based PID controller present in the system without EVs. In both, particularly microgrid source control and EV control, you can see here clearly genetic algorithm is giving a better response in terms of overshoot, undershoot, and setting time. So only frequency responses I have taken here. So why we can say ask it because this is only the deviation frequency, the area control area is a change in frequency. So here you can say with a different EVs combination. Already I told you we have taken 3 scenarios: 80 number of EVs, 160 number of EVs, and 300 number of EVs. So here 80 number of EVs we have taken, and we are again comparing all the controllers, particularly with the PI, PID, and this is the what manually parameters we have just put in, particularly when there is a genetic algorithm is not there used, and there's a GA based PID optimized controller with the 80 number of EVs. We can see here again the red line is presenting the better response, and you can see here is 0.04 is your particularly big overshoot, and you can see here it is a less than about 0.27 something. It is a big overshoot. Undershoot also is a near about 0 is less, and if you're talking about the particular settling time, it's almost with the GPID. It's near about whenever it is coming to particularly 18 or 19, it is around 16 seconds. It is particularly optimized or settled. So fine, we can, whenever we're talking about the 160 number EVs or 300 number of EVs, also you can go and compare with the 1% SLB, and you can also see the particular responses. Here also we are just observing the system responses with the 1% deviation. So it is clearly seen that 160 or 300, whatever is there particularly, we can say that particularly here overshoots are reducing. You can see here is a 0.04, here 0.27, here is a less than 0.02. Here you can say it is less than 0.15. So overshoot is reducing. Settling time is almost the same in all cases. So this is the values are taking here. Overshoot, undershoot, and whatever the comparison here we have taken the values. GAPID with a particularly 300 EV just showing better improve the stability in comparison to other combination with the less setting time, and particularly the big deviation, mainly overshoot, because undershoot is almost here. You can see it is a 0, near to 0. So next thing is what we have taken one random load pattern, and we are checking the particularly what are the system stability here. Same thing, the random load also clearly visible, that particularly the GPID with a particular EV just showing better responses in comparison to without EV. So same different scenarios we have studied here with the 80 numbers of EV with the both EV aggregator combination is so repeated. Okay, so this is the 80 and you can say this is the 300. And again, it is a clearly visible that particularly EV with the 300 with this particular random root pattern also is showing the better responses in comparison to particular other combinations. So this is with the different load perturbation, 1%, 3%, 5% with the GA PID or optimized PID controller with 300 EV present in the aggregator. So we can say here particularly, so almost you can say in SLP 1%, 3%, 5%, certain times all have the same. Only a small deviation is there in the overshoot and undershoot. But anyway, you can say that particularly GPID with the EVs are giving a controlled or it is reliable with the different loadings means what disturbance scenarios. No need to change again. So without optimization with the 3%, 5%. With respect to particular 1% load disturbance, whatever the optimized value we have gained, with based on the same parameters we have given 3% and 5%, only disturbance changed, and we are checking here particularly how the system is responding. So this is again the same scenarios, particularly 50% loading with the 30%, 80% load change. We have done that particularly. Here we have taken whatever the 50% loading with 1% SLP, 3% and 5% SLP. Here for the random load job, whatever we have done, we have just increased the load by 80%, from 50 to 80%. At the 80% of the system loading, how the system is responding with the presence of G-optimized PID controller and EV300 number of EVs are present. And also we have reduced the load up to 30% with a 30% system load, how the system is responsive. Here you can say this particular controllers are acting very precisely, or you can say that it is a very robust or sensitive but robust controllers with respect to changing particularly loading conditions of system loadings also. So both disturbances, different disturbances and different loading condition, we gave the same controller gains with respect to the base one of 50% loading with 1% SLP, and we have checked how our controller is responding. So can you observe here? So almost near about the same. So it can also control particularly up to 80% loading condition higher side and 30% loading condition in the lower side. So representing the particularly a stable system for the different disturbance condition and disturbance loading conditions. So these are the planned with system EV aggregator, particularly the values we have taken here with the EVC without EV. EV0 means without EV, 80 number of EVs, 160 number of EVs present in the aggregator. 300 EVs are present in the aggregator, different gain values are here. So particular whatever the already I have discussed, whatever I've discussed, particularly with number of EV, whatever we have seen, the system is getting a better stability in particular, and also fast frequency controllers less setting time it is settled after getting the adjustments. Also with the different loading conditions also in presence of EVs. Anyway, a controller is there for the controlling of the deviation frequency, but anyway, system, with the presence of EV also system improvement is there. Whatever we have just discussed without EV and with EV. So here the references are there. Mainly what I just say in this is particularly the studies, particularly in presence of EV system is improving here with respect to what at the microgrid side the generation is available and also main grid side. So here also particularly scope is there for particularly energy management, and also scope is there to different controlling techniques also you can use. Mainly model prediction technique. It's a centralized technique, model prediction technique if you go. And if you go to decentralized control, so this primary and secondary control mechanisms are also there. You can also this word go for the application of different controlling mechanisms. Also fuzzy control is also there, very precise controlling will show. So these are the things that there, and also here a simple microgrid is grid connected microgrid is there with the EV. Also EV side, the aggregator side, also so many means what scope is there in research, particularly using the machine learning technology with the real time, how many EVs are there, how to make the data, particularly charging, discharging, how to choose the number of EVs, particularly while participation in there, and how much load it is, power it is taking, absorbing for the charging purpose. That is also another one study on with respect to how to maintain the system stability and reliability at that time. And also second thing, whenever how much power is available or present, means what presently available to support the grid at the time of high load, means what peak demand conditions. There also you can go for the another research. The scopes are there. Demand side management also there is a research with respect to demand side management, how we're going to manage your EVs and also microgrid or different multi sources present in the system, different control with the respect to different control technologies and optimization techniques. So many scopes are there for the research. So, any questions?
I request participants to post their queries. You can post in chat box as well if you're having any queries. I think there are no queries, ma'am. I'll just ask a query regarding multi-input converters for DC microgrid. When we are using multi-input converters for DC microgrid, which type of control will be better? Because we have discussed about primary, secondary, and tertiary control methods. So, which method will be appropriate for multi-input converters?
Well, we will go for the multi-unit control, so controlling so many controlling technologies there, fine. So in that, it's better to go for master slave control instead of primary, tertiary, and secondary. This is the basic master slave control may be there, and also model predictive control mechanism that is based on artificial intelligence AI. So those will be giving a better opportunity. I'm talking about the research.
Yes, ma'am. Yeah, group control is there, no,
In
ma'am.
that,
In that also
you
can we employ AI? We have group
Yes,
control,
ma'am.
right?
Yes, ma'am. Group
Can we
control also you
employ
can go for
AI
the
in that group control?
AI in the sense what either you can go for the neurofuzzy controller or fuzzy controller. So artificial machine
Okay.
learning or artificial intelligence, if you can say that with the different scenarios, first you have to make so many case studies. You have to particularly collect the information about the system voltage profile, real power, reactive power, with the different type of fault condition, different type of disturbances and all. You have to make your database. With respect to that, you have to give a comment. So those are the little bit of different field. So scope is there.
Huge
So instead of
database is
optimizing,
required. As you
yes,
told,
ma'am.
like
You have
case
to,
study has to be done on that.
yeah, you have to make your system. You have to create different case studies for your system. You have to collect the data. Then you have to put your logic. That means what if the scenarios will be there, values, parameter values will be there. So no need for any optimization there. So your logic and your program will be decide how much error or what is the limitations particularly. So with respect to that, it will choose the parameters automatically. Your system coming into stable conditions.
Okay, ma'am. Any more queries from the participants? I think there are no more queries, ma'am. I would like to just wind up the session. So since this is the last day of the event, I would like to thank few people. So I am Dr. R. Amleswari, Assistant Professor in Tripoli Department and Faculty Coordinator of this FDP. So firstly, I would like to thank all the participants because we have participants from 7 states who have registered and attended this event. So I hope this it will enhance their knowledge and also boost many of their research work, because all the topics are research oriented. As you have discussed today, all the control strategies, there is a much scope to do their research. So I would like to thank the college management, Chairman Sir, Shri Satyanarayan Raju Sir, Secretary N. Prasad Raj Garu, and Treasurer N. Kanakaraju Sir, and Director Dr. J. Raja Murugdas Sir for giving us permission and supporting us by providing all the necessary resources to conduct this FTP. So next, I would like to thank our today's speaker, Dr. Pooja Das ma'am, for accepting our request and presenting here, ma'am. Thank you very much, ma'am.
Thank you.
And I would like to thank the remaining speakers also, Dr. Gururaj sir from IIT Kanpur, and Dr. Srijit sir from NIT Silchar, and Dr. Hemachandar sir from NIT Pondicherry, and Dr. Srinivas sir from Tata Elxsi in making this event a grand success. So I thank our HOD sir, Dr. R.S.R. Krishnam Naidu sir, who continuously motivates and encourages to conduct such type of events. And I also thank the entire faculty who worked very hard in getting the registrations done, because we had a short period, and they supported in all the ways needed in making this event a grand success. Last but not the least, I would like to thank Chendu sir from IT department, who continuously monitored and supported us with a good internet connectivity, because since we are having all online sessions, so that we did not have any glitches in this event. So I thank one and all who directly and indirectly supported us in conducting this event and making this a grand success. Thank you, ma'am, for making your day and giving your valuable time to present here in this event. And we look forward your presentations in our coming future activities also. Thank you very much.
Sure, madam. Sure. Thank you, ma'am. Thank you. May I leave, ma'am?
Yes, ma'am, you can leave, ma'am.
Thank you.